At this point, we're ready to plug our trig functions into our sigma f equals ma equation, but we've got a problem. The graphs we've seen up till now have had position on the y-axis and time on the x-axis. But if we think about trig functions, they're not a function of time, they're a function of theta. So we have to find some way to convert theta, an angle, into time. And the way you do that is to come up with the idea that one complete period, what you get when you go back to where you started, which is to here, consists of 2 pi radians and a time capital T. So you can almost make a conversion factor. If I multiply whatever time I've got by 1 over the period, I get the fraction of how far through a period I've gotten. And if I multiply by 2 pi, I turn that into an angle. So having this guy here lets us use sines and cosines with time. It's a conversion factor. Remember that you can actually do a rotational version of all this too. So you can actually have angle as a function of time. And the same thing applies, even though we expect sine to operate on, say, an angle, we can convert how far you are through the period in angle to how far you are through the period in time, because one period is t seconds and 2 pi radians. What's strange, though, is that then theta goes on the y-axis because you're talking about what direction you're pointed in. So x and theta are interchangeable, as they often are. So there's our function of theta or x with respect to time. So what we have to do now is we have to figure out how to take its derivative. And if it just said a sine x or a sine q, if it was just one variable, this would be easy to do. But we have to think about how to take a derivative of a trig function when there's something in it. And to do that, we have to use what's called the chain rule. The chain rule works by a pretty simple algebraic trick. Let's say I want to take the derivative dy dx, change in y over the change in x. But I can't do that. But let's say there's some other function I can easily take the derivative of, like the change in y over the change in u. That will be equal to the change in y over the change in x if I can also take the derivative of this variable u with respect to x. Because if you multiply these two together, you just get back to dy dx. So what this allows us to do is to break a complicated function into pieces. Instead of taking one derivative that's hard to do, it lets us take two derivatives that are easy to do. Now I have to show you what I mean. Again, if we were just trying to take the derivative of sine, it would be super simple. So what if we can take our complicated function and make it this simple? So here's how we do that. We're going to make up a function u equals 2 pi over period times time. Notice that's the inside of our trig function. That lets us write our trig function as simply a sine u. We've subbed in this new function. Well, we know how to take that derivative. That's pretty simple. It's just a cosine u. Now that's not the thing we want. We want d theta dt. But we're partway there. We can use the chain rule to get that. What we then have to do is take the derivative of u with respect to time. And that's pretty easy. The derivative will just be 2 pi over t. T to the 1 turns into t to the 0. So we're just left with 2 pi over t. So that means the derivative we actually want, d theta dt, we just multiply those two together. And basically, the thing inside the trig function, 2 pi over t, pops out. So we just have an extra factor of it on the outside. We could then play this game again, and we could get the derivative of omega, which is alpha. Let's see what that looks like for x, v, and a in linear motion. So I've got those functions up on the board, and hopefully you can understand the calculus that produced them. But if not, it's really worth learning what the position function and the acceleration function look like. They're very similar. There's this constant on the front of the acceleration one that's because of the chain rule and taking this out. But the bottom line is they're directly proportional to each other. We now can use our original Newton's second law equation that we wrote for this particular force situation and these two periodic functions for position and acceleration in order to solve for period. It's actually a pretty easy solution. So you always start by doing sigma f equals ma. You plug in your forces and you get to this situation where x is directly proportional to the second derivative of x. Or theta is directly proportional to the second derivative of theta. So I'm going to take that, I'm going to copy it, but I'm going to plug in what I have here. So negative k, and for x I'm going to plug in a sine 2 pi period, or period times time. And that apparently equals mass times negative 4 pi squared period squared a sine 2 pi over period times t. So we get a huge amount of canceling here, including all the trig functions. So the negative becomes positive. The amplitude, which we never even knew anyway, is gone. The sine function is gone. And we're left with k equals m times 4 pi squared over period squared. So now what I'm going to do is solve that around for period, which is what we usually want to get when we're measuring repetitive motion. I'll multiply both sides by t squared. So we have t squared times k equals m times 4 pi squared. Divide both sides by k. So I have t squared equals 4 pi squared m over k. And of course my last step will be to square root. And I'm left with the equation period is 2 pi square roots of m over k. And that's what gives us the dependence that we saw in Dr. Hume and Dr. Ivy's experiment, where it depended on mass and the stiffness of the spring. We'll play this game for all simple harmonic motion cases. You'll see others, pendulums, physical pendulums, possibly torsion pendulums. Again, it all starts with this dependence and plugging in these two functions.